Welcome to Complexity Made Simple. My name is Paul Allen and the subject of today's newsletter. Well, we're going to take a look at how using MSA, Measurement System Analysis, can improve your CPK, and why actually the only time to really concern yourself about the MSA results is when this is exactly what you're trying to do. So we're going to take a look at measurement system analysis, and how it can improve your CPK. Okay, so before we take a look at an example, so we're going to take a look at an example in an Excel spreadsheet using some SPC Excel software. We're just going to consider what measurement system error is doing to your results. So here's technically what's happening. Your process produces results. These are the process results in the black. And of course, you'd like to see these results and you'd like to compare them to the specification. See how you're doing. So of course, the next thing you've got to do is you've got to put the parts through a second process. You put them through the measurement process. Now, unfortunately, the measurement process also has variability in it. So whilst you would like to see the black distribution, you are never going to see that. So you have to give that up, because what you see are these two added together. Now, what does that mean? Well, it means that you always see something which is bigger. It's got more spread, more variability than what was originally there. So this error is inflating your variability. It's making your tails look longer on your data set. Now, what could this mean, of course? Well, if you drop tolerances on there, it's going to make you think. It could make you think you've got defects and you have no defects at all. Depends how bad the effect is. If the inflation is quite large, then it could certainly make you think defects that aren't really there. But it could also just inflate your defect rate. So it could just be that it's going to inflate the defect rate and make it look as if you have more defects than you really have. So you can see, doing an MSA, understanding, because this is what the MSA does basically, it tells you how big that is. So if you're trying to solve a defect rate, if you're trying to understand how to make these tails come in, understanding how to get the tails to come in using the measurement system error, this could be, it could be part of your solution. To be honest, it could be the whole solution. So, you know, you could have a situation where your process is really very, very consistent. Your measurement system, unfortunately, is terrible. And you see this, you see defects, when actually there's no defects there. Now, that's a particularly bad case, but this is going to tell you what this picture looks like. That's what an MSA is for. It's to tell you how much variability you have in the process. And one last thing to say, of course, and this was something I said at the beginning, you only really need to concern yourself with the MSA results if you have poor capability. If you have a situation that looks like this, highly capable process, you are going nowhere near the tolerances, then even if you have, I'm going to draw the distribution inside that, even if you have a particularly poor measurement system and it's inflating the variability of the results, how much pain is it causing you? Well, it's not causing you any pain. Will you misclassify good parts as bad? Well, no. Will you think you have a defect rate that isn't really there? Well, no. So even though you didn't get a good result from your MSA, does it really matter? Well, actually, no. You know, if this thing shifted all the way over here and started to produce defects out here, would your measurement system spot that? Yes, it would. So, to be honest, your measurement system is doing what you need it to do. It's discriminating between good parts and bad parts, and it can see dramatic shifts in your process. So your measurement system actually is doing okay, even though the MSA results in theory might say, you've got a poor measurement system, you should do something about it. It's not necessary to do something about it when your capability is good. This is when this helps you solve this problem. So what does an MSA actually look like? Well, it's looking for variability in your measurement system. It's trying to quantify how much variability there is. And you're just going to do a very simple thing. You're just going to take a part. There's obviously a feature that we're interested in on that part. In this case, I'm just going to say it's the diameter of the part. What you're going to do is you're going to identify an operator, somebody who measures, a measurement system, call it what you like. And then what you're going to do is you're going to give them that part not once, but twice. So you're going to give them the part twice. So they're going to come up with an answer. I'm just going to write something down as an example. So the first time they measure it, they get 623. The second time they measure it, they get 621. Now obviously, they measured the same part twice. These should be identical. Any difference is this. It's measurement error. It's extra variability. Because the part at this point isn't moving, but we're getting extra variability from the measurement system. Okay, now one thing that's very important, when you give this part to this operator, they mustn't know that this is the same part twice. So you're not just going to give them one piece, you're going to give them multiple pieces. In fact, the suggestion normally is that you give them 10 pieces to measure. Then what you'll get is you'll get them to measure 1 to 10 in the first round. The second time you ask them to measure, you'll give them back to them in a random pattern. So they won't remember, they won't know that this is part number 1 in their hands, therefore they won't remember 623, therefore this second measurement will be a clean and clear measurement as if it's a brand new part with no operator bias. Now the parts that you select here, these parts here, you must select them randomly from a normal batch, so that what the operator is seeing is just the natural spread of parts. So there's no pre-selection. You're not picking all good ones for them to measure or all bad ones for them to measure. Okay, so this is a random selection of 10 parts. You offer them to them 1 to 10, then you offer them back in a random order. Now obviously, any difference here is error, measurement error. You can call measurement error extra variability, because that's exactly what it is. It's extra variability. Now, having given the parts to system number 1 or operator number 1, we are then going to give them to another operator or another measurement system, and we're going to get them to do the same thing. They're going to measure the same part, and you're going to get 2 measurements for them. And of course, any difference that you see, is error. Now where we're seeing error inside operator 1 and error inside operator 2, this is known as within system. And they call within system, another name for it is they call it repeatability. The ability of a measurement system to repeat its own results. So we're asking the question, can operator 1 agree with itself? Can operator 2 agree with itself? Yeah, so that's the first level of problem that you have, repeatability error within system. But of course there's also the problem of these two agreeing with each other. Now what we do here is we work out the average. So the average up here, for instance, was 622. The average up here was the same, 622. So you can see here we don't have any error. We have error within system, but we don't have error between system, for the example that I've put up here. So this is between system error. And between system is known as reproducibility. Okay, so you have this thing, they call it gauge, R&R, and it's these two words, repeatability and reproducibility, within system error, between system error. And that's what the measurement system analysis is going to find for you. It's going to tell you how big this is, and then it's going to tell you where's your biggest problem. Is it within or between, or is it a bit of both? But you take 10 parts, because what you're going to end up with ultimately is 40 data points. Each system has measured 10 parts twice, and we end up with 40 data points. Now of course you could keep going. If you've got 3 shifts, 4 shifts, 5 shifts, you've got a room full of technicians and you want to test whether they can actually measure stuff or not, you could make this much bigger if you want to. My advice though is the bigger you make it, the more difficult it gets to see what's going on. So initially a good thing to do is to just stick with maybe 2 people or 3 people, maybe your most seasoned technician against the junior technician. Maybe you do that, but I would normally just do 2 or 3 measurement systems. Any more than that and it starts to get way too complicated. So what we're going to do now is take a look. Okay, once I've got these 40 data points, what do? How does the software deal with it? What am I actually looking at? So we're going to take a look now. We're going to go onto the computer and look at an example. Let's take a look. Okay, so here we are, look. We have a template set up, and this has been set up by SPC Excel. So I will have gone gauge capability, look, create template, and then it says how many operators do you have? 2. How many trials did they do? 2. How many parts have they got? 10. And then I've put a specification. Now I'm going to suggest in this case this is millimeters. This is a little example where we've measured the diameter of some nails. So it's a little exercise that we do in class in order to be able to demonstrate the use of SPC Excel. So there's the data. Now the one thing I do before I do anything else, I'm going to just eyeball the data. What does it look like? Does it look sensible or not? So when I look across here, you know, I can see 639's the top, 629's the bottom. So I've got 0.1 of a difference in the measurement of the same part, the same nail. And you'll get a sense as to whether that's acceptable or not, just using your common sense initially. We're obviously going to use some mathematics to help us, but just use your common sense, just observe and see if you think that what you're seeing makes sense. You know, 6 millimeters here compared to 588 there, operated to for the same nail. You know, is that acceptable? Is that an acceptable kind of, or is it an expected change even? You know, so use your common sense, nothing wrong with that at all. But now what we're going to do, having got the data, we're going to go gauge capability, and we're going to click on the ANOVA. Now I have two choices with this data set. I could go ANOVA and I could go X bar R analysis. They are two different ways of coming up with the same quantification of the problem. The one that's recommended and the one that's much more reliable, they say, is ANOVA. So that's the one I'm going with. Okay, now then, I've got a table of numbers, but I've also got at the bottom, look, graphs all the way across here that are telling me stuff. Okay, so what I'm going to do, I'm going to walk you through the way I use everything that's just been put in front of me. So the first question I've got to ask is my measurement system any good? And the way I'm going to answer that question is with these two numbers that I've just placed in the yellow fields right there. Precision to tolerance versus precision to total. Okay, precision to tolerance versus precision to total. Now let me show you on the whiteboard what these two numbers actually mean. Okay, so precision to tolerance, precision to total. Precision to total is basically saying, how big is this? And it just says, as a proportion of the total. So you're looking at the total variability. How big is that? We'll call that A. We'll call that total variability B. And all it does, it simply divides A by B, and you come up with a proportion. So if it says 0.1, what does that mean? 10%. So you've got an extra 10%. That's precision to total. Precision to tolerance, on the other hand, it says, well, how big is that compared to my tolerance? So now it's looking at this width here. It isn't looking at the total width. It's looking at the tolerance width. And basically what it's asking you is this: how much of your tolerance is being consumed by measurement error? And again, you'll get a similar number. You might see something like, I don't know, 0.21. What does that mean? Well, it means 21% of your tolerance is being consumed by measurement error. So your manufacturing process has only got 80% of the tolerance to get into. So they're the first two numbers: precision to total, precision to tolerance. And they're telling me if my measurement system is any good or not. What's my target? On both of them, I'm looking for 10%. I'm looking for 0.1 on both of them. Let's go back to the exercise and take a look. Okay, so my precision to tolerance, precision to total, you can see that they're not meeting the 10% rule. They're up at 0.4 and they're up at 0.24. So of all the variability I can see, 24% of it is measurement error. Yeah, so I'm getting an extra 25% on the width of my distribution. And I'm actually using up 40%, 42% of my tolerance is being used up by this measurement error. Well, now what I need to do, of course, I need to find out where my problem is. So with an MSA, is my measurement system any good? Is question number one. Question number two, where is my problem? And then question number three is, what am I going to do about it? So now, having answered the question, is my measurement system any good? The answer is no. Well, okay, where's my problem? Well, what I'm going to do, I'm going to look at these two numbers up here. Look, I'm going to put them in a slightly different color. So let's put them in the orange fields. Now you can see that's sitting against repeatability and reproducibility. And I'm just looking at their size against one another. So that's the amount of standard deviation. That's the amount of variability that's being contributed by the measurement system, by repeatability, by reproducibility. And you can see, look, that repeatability is 3 times bigger than reproducibility. In other words, my problem is within system. It's not between systems. Okay, so that's what it's telling me. So is my measurement system any good? No. Where's my problem? It's a repeatability problem. Now let's take a look at the graphs. So if I take a look at the first graph, now this is plotting the averages. So of course we want to see the graph to look like this. Both graphs for operator 1 and operator 2 go up and down together. It's a great sign. The other thing is that they're not very far apart, so there's a tiny little bit of gap between them, but they're following the same pattern and they're close to one another. A perfect graph here would be they were over the top of one another. Okay, so we know that that's not our problem, so let's move on. Now what I'm going to do is move all the way to the last graph. This is a range graph. Now this is the difference between the first measurement and the second measurement for each operator. So the blue line was operator 1, the brown line is operator 2. Perfection here, of course, would be both lines lying at 0, because that would say there is no difference between your first measurement and your second measurement. Now what we've clearly got, look, is operator 2 is showing much more variability than operator 1. So when we go, is your measurement system any good? No. Where's my problem? It is within system. What am I going to do about it? Well, maybe I'm going to give operator 2 some more training. Maybe I'm going to come up with a better standard operating procedure so we can train people better and not rely on skill perhaps. But this is essentially what an MSA does. Now I've missed out some other charts. There is only one other chart that I find useful in SPC Excel when we do this, and it's this one. Now this is the misclassification rate, and what it's telling me up here, look, if I look at the misclassified parts, let's blow that up and make it a bit bigger, is it? So if we take that up, it's saying, look, 309,000 parts in a million could be misclassified. In other words, 30% of my product could end up being misclassified with this measurement system. So good parts could be assigned to be bad. Bad parts could be sent to the customer. So this is to help you to understand what risk you take if you keep using this measurement system as it currently is. So currently, we'd want to improve this process. The error is within system. We'd want to improve operator 2, but we'd probably want to improve operator 1 as well. So maybe a standard operating procedure might help us to understand that. Maybe a better piece of equipment. I mean, you might decide that this is a standard piece of equipment like a micrometer or a vernier, and maybe you decide you want to create a specialist measurement jig. It makes measurement easy and more repeatable. You might decide that that is the answer to your problem. But there's the way I use MSA. Is my measurement system any good? And I'm looking at the data for that. Where is my problem? And I'm looking at the orange data for that. And then I'm looking at the graphs. The first graph, the last graph, and finally the misclassification graph. And that is the way that I use MSA. Okay, hope you found that interesting. Now, what will that give you if you use MSA to do this course? What's going to happen? Well, what's potentially going to happen, of course, if you can improve your measurement system error, you will drive that blue distribution in without touching the process. You're not out. It's a big, ugly manufacturing process. You're just looking at on the table. You're just looking at how to measure it. So you might bring those tails in, you might destroy your defect rate. And how much work have you had to do on the process? Absolutely not. You've had to just work on the measurement system. So that's how influential it can be. I mean, I'm not saying it will be as easy as that. It could just be that you do a little bit of MSA work and you cut the end off that tail. Still got some defects, but that might have halved your defect rate. Then you have to get rid of the other half of the defect rate by working on the manufacturing process. But the measurement system can sometimes be a fantastic help in getting rid of your defect rate. And that's why you should use your MSA to improve your CPK. But if you've got this, if you've got a fantastic CPK, don't go worrying about your MSA results. Don't go saying, oh, I haven't got a good measurement system. It doesn't pass the rules. Now, I know it doesn't pass the rules, but it's not giving you any grief. Don't give yourself a problem that doesn't exist. That's most important. But if you use MSA, you can improve your CPKs and you can make pots and pots of money.